Hello and welcome to lesson 2 of this chapter, which is 5.2, the definite integral. So last lesson we talked about finding the area under curves by breaking up the area into a bunch of smaller rectangles. What we're going to be looking at now is what happens if the number of rectangles approaches infinity, or if the width of the rectangles approaches 0. How will that affect the area? Well, we know that the more rectangles there are, the closer we are going to be to the actual area under the curve. And the idea that we have either our number of rectangles approaching infinity or the size of rectangles approaching 0 means that this is called a Riemann's sum. So we have here that we have the sum of all of our rectangles. So if you recall from last day, when we had a rectangle under the curve, the width of the rectangle was delta x, and the height of the rectangle, either right endpoint, left endpoint, or midpoint, was f of ci. Okay? Ci being whatever iteration of rectangle you're on. So for the first rectangle, you'd be at C1, second rectangle, this was C2. We can use x's as well, like f of x1, f of x2, etc. So this is called a Riemann sum when you take all of these rectangles and you add them up. In that, we have this delta x, which was our width of our rectangle, and we know that this was b minus a over n, b being the end point, a being the starting point, and n being the number of rectangles. Now there's another new notation here for our delta x that you'll see, which is this delta in these almost double absolute value brackety looking things. It's just another notation, but it's referring to the same delta x that we've been referring to as we go along. So the definition of a definite integral is this idea that as we increase the number of rectangles or decrease the width of those rectangles, we will approach the exact area under our curve. This is defined as a definite integral. We have a lower bound A and an upper bound B. This funny looking S thing is the sign for integration. And we say that a function f is defined on an interval a to b, and if the limit of the Riemann sum exists, meaning we can actually find this limit here, then f is integral on a to b, and we denote the limit by this. So this is saying, basically, the limit as your delta x approaches 0. So the width of the rectangles is approaching a very, very small number, almost to be towards 0 width, meaning you would have a lot of rectangles. The sum of the areas of those rectangles, so remember each one of these is one rectangle. The sigma notation here is telling us to take the sum of the areas of each of those rectangles, and we are taking the limit as the width of those rectangles approaches 0. If we can find that limit, then we say f is integral, and our integral is this portion here, which is the function f with our dx from a to b. This limit is called the definite integral of f from a to b. The number a is called the lower bound or lower limit of integration, and b is the upper bound or upper limit of integration. Now, this is not the limit you will use most of the time. Another way of writing this, if we think about it in terms of the number of rectangles, is the limit as n approaches infinity, the number of rectangles approaches an infinite number, and you take the sum of the areas of all of those rectangles. And again, to find the area of one rectangle, we would do f of ci times delta xi. This is also equal to our integral or our area under the curve. So what an integral is an area under the curve of f of x. For a definite integral, you would have a lower bound and an upper bound, or a lower limit of integration and an upper limit of integration. A we usually denote as the lower and B as the upper. So as we continue through this chapter, we will be starting to take integrals of various functions and learning different techniques of integration. Basically, how can we calculate the area under all of these different kinds of curves that we might have? And we do definite ones and indefinite. Indefinite just means we don't have an a and a b there, and our answer is a function and not a number. Okay? So we have to remember every time we do an integral, what is it we are actually doing? What we're actually finding is the area under the curve. Something to note is that if you have a continuous function on our closed interval, then f will be integral, meaning you can take the integral of f as long as f is continuous. Continuity implies integrability. Okay? And if you think about this, the reason why if it's discontinuous, it might not be integral is because if you have something that looks like, let's say, this, if our A is here and our B is here, we don't have an area under the curve because this would go up forever and down forever. And so we can't calculate that area because that area does not ever stop. It would keep going down and keep going up forever. Okay? So we cannot find an area under our curve for something like this. That would be a discontinuous function. If we change our B to be closer so that this same function is now continuous, for example, if I put b here, that means I have an area under my curve that I can calculate. So we're going to try and do this question. We're going to evaluate the definite integral. Okay. Our lower bound here is a is -2, and our upper bound b is 1. We need to remember that if it's asking us to find the integral, this is the same thing as asking us to find the limit. As n approaches infinity, the number of rectangles approaches an infinite number of the sum of all of the areas of our rectangles, our many, many rectangles. So we have to remember too that our delta x is b minus a over n. In this case, b minus a would be 1 minus -2, which gives us 3 over n. If we choose our ci to be a right endpoint, then ci is equal to a plus I delta x. If we choose a left endpoint, then ci would equal a plus I minus 1 delta x. And if we think about this and break it down, this makes sense. This means that if I start my rectangles at the lower bound a, right? So let's say I had, I don't know, some curve, okay? So if I start my rectangles here, our first rectangle would look something like this. And if it's a right endpoint, then that is the height of the rectangle that we are referencing. And so remember the height of this rectangle here, f of xi, well, this xi value would be equal to a plus delta x, but there would only be one delta x. If we choose another rectangle, this one is now another xi. So let's make this x1. So then this one would be x2. So we would have f of x1 here. This would be f of x2. x2 would now be a plus 2 delta x. If we had an x3, that's going to be a plus 3 delta x. So we get a plus I delta x. So let's remove all of this because we're going to need this space. So we need to figure out what our ci is going to be so that we can find f of ci so that we can take the sum of all of our little rectangles, and then we can take the limit of that sum as the number of rectangles approaches infinity. So a is our lower bound, which for us equals -2. Delta x we know is 3 over n. So we are going to have -2 plus 3i over n. We know that our f of x is equal to 2x. And so f of ci is going to be 2 times negative 2 plus 3I over n. Now, if we want to find the integral, we're doing the integral from negative 2 to 1 of 2x dx, which we know should equal the limit as n approaches infinity of the sum of all of our rectangles. So we end up with 2 times negative 2 plus 3I over n is our f of ci, times delta x, which is 3 over n. And now we're going to have to do some work. Okay? We need to simplify this giant sigma expression so that we can take our limit. So let's do limit as n approaches infinity. We have 1 to n. Let's change this to be negative 4. We could expand all this out, but n, we know, is approaching infinity, right? Our I is what's changing inside of our sigma. So within the context of the sigma, the n is constant, both 2's are constant, the 3 is constant. Within the sigma, the only thing that's changing is the I. The n is only changing within the limit with our n approaching infinity. So we can actually take this 3 over n out and the coefficient of 2 in the front out to have 6 over n. So I'm taking this and this as constants just to put them in front of the sigma here. And then we get negative 2 plus 3I over n. We can break this down. This can be broken down into the sum from 1 to n of negative 2 plus the sum from 1 to n of 3I over n. And now we need all of our information about sigma notation to break these up. We know that the sum of a constant is that constant times n. This 3I over n, we can take the 3 over n out and have the sum from 1 to n of just I. And then we can take the sum of I, which we know to be n times n plus 1 over 2. And then we can simplify. So we can have these n's cancel out. We can expand this back in. We can expand the 3 into this n plus 1. There's a bunch we can do here. So let's go back up here. Have the limit as n approaches infinity. We're going to end up with negative 12 because our n's will cancel out here when those expand in. And then we'll end up with 18 times n plus 1 all over 2, which gives me the limit as n approaches infinity of negative 12 plus 9 times n plus 1, which gives me the limit I should have an n on the bottom here, as n approaches infinity of negative 12 plus 9n plus 9 over n. So let's make a common denominator here. This is going to be negative 12n plus 9n plus 9 over all over n, which gives me the limit as n approaches infinity of negative 3n plus 9 over n. Now the limit as n approaches infinity of this stuff should give me negative 3. So a reminder that if you have approaching infinity, you're taking the highest power on the top, highest power on the bottom, you make a coefficient, take the coefficients of each of those to make a ratio, and that would be your answer. And if we look at this algebraically, we could actually calculate, because this is a straight line, 2x is a straight line. We can see this diagram here has a bunch of rectangles. This is a finite number of rectangles. Our number of rectangles is approaching infinity for our question. And so the idea is that the more rectangles you have, the closer you're going to get to the actual area under your curve. Note that definite integrals can be positive, negative, or zero. In order for a definite integral to be interpreted as an area, the function must satisfy the conditions given in the following theorem. Okay. So f must be continuous and non-negative on the closed interval, a to b, then the area of the region is bounded by the graph f and the x-axis and the vertical lines x equals a and x equals b. Then the area is equal to our integral. Okay? So basically, in order to be using this area idea, we have to actually be able to find a finite area. Okay? So that means that we are having a starting point, ending point, and we draw vertical lines there. We bound by the x-axis, and then our fourth side of our object is basically our curve. Okay? So again, we've got our Riemann sum, which is the limit of a sum of areas of rectangles, and that can be defined as a definite integral. And in order to think of this as the area of a region, we need to actually be able to draw in a region, basically. Okay. So we're going to try this next question. We'll show algebraically how it works, and then we're going to also draw in the object. Okay. So we are going to evaluate using a geometric formula. So if I think about this, our lower bound is 1. Our upper bound is 3. We're going to bound by the x-axis as per the theorem above. Okay. And then our extra side is going to be the function 4, which basically means f of x is equal to 4, or in other words, you have a horizontal line at 4. And so the area bounded by these 4 lines is this lovely square. Well, if I want to find the area of a square, the height of this square, or it's not actually a square, it's a rectangle, is 4. The width is 2. So the area is 2 times 4, which gives us 8. So the integral from 1 to 3 of 4 is equal to 8. So some special definite integrals. If f is defined at x equals a, then the integral from a to a of f of x equals 0, which makes sense. You'd have no area if you start and end at the same point. Okay. If f is integrable on the closed interval a to b, then the integral from b to a of f of x dx is the negative of a to b of f of x dx. So basically, if the bounds are backwards, it essentially means that you're now viewing your area in the wrong direction. So to switch to be the right direction, you can switch your bounds, and that would be the negative version of going in basically the wrong direction. So when we read graphs, we usually read left to right. So our lower bound should be on our left, our upper bound on our right. So if for some reason the integral is written backwards, being the lower bound is on the right and the upper bound is on the left, you can rewrite it so that they're in the right direction as long as you take the negative of that integral. Okay, so let's try one. If I want to evaluate sine x dx, the integral of that from pi to pi, the first thing is that f has to be defined at x equals a. So is sine x defined at x equals pi? Yes, it is. Sine of pi is equal to 0. It's defined. It equals 0, but that's okay. So therefore, the integral from pi to pi of sine of x dx is equal to 0 by this special property. So some additional properties to help you solve definite integral questions. The additive property says that if you have an integral from a to b of f of x dx, you can split that up to be the integral from a to some extra number c, usually in the middle of our integral, plus the integral from c to b of f of x dx. So what that might look like is something like this. Maybe our a is here and our b is here. So in order to calculate the area, we might say, okay, we're going to do an extra c. We're going to do this area. plus this area. Other properties, if you have the integral from a to b of c dx, okay, this is equal to c times b minus a, so a constant. So that's like the example that we just saw. If we have our a and our b, our x-axis, c is just a constant. So the area under there is going to be the height, which is c, times the width, which is b minus a. Therefore, our area is c times b minus a, and the area is our integral. If we have the integral from a to b of a constant times a function, that constant can be brought out of the integral the same way a constant can be brought out of a limit. Okay, so if you think about that integral in terms of the Riemann sum, the integral is just the limit of infinite rectangles, the sum of all the areas of infinite rectangles. So if you take the constant out of the limit, that would be the same as taking your constant out of your integral. And if you have two separate functions, adding or subtracting, you can break that integral up into the integral of the one function plus or minus the integral of the other function. The other one is preservation of inequality. So if f and g are two integrable functions on a closed interval a to b, if f is smaller than g for every x, then the integral of f will be smaller than the integral of g in that interval. And if you think about it, well, if f is smaller than g, if you have something like this, is your, let's say your g, and let's say your f is something like that, well, the integral of f is the area under f. The integral of b or g is the area under g. So if g is larger than or equal to f, then the integral of g must also be larger than or equal to f. Okay. And that is it for this section.